Hello, all of you. Good morning. Tough Corona times going on everywhere, and every doctor speaking about immunity, boosting the immunity, and you all know our brain is the master gland. So to improve our immunity, let us be very positive. So that positive brain definitely secretes all the required hormones, and our immune system will definitely boost them. Right? Last class we did our rapid revision of current electricity up to the concept of Kirchhoff's laws and Resistor bits. And today, one more important topic, that is measuring instruments, the ammeters, voltmeters, the case of ideal voltmeter, which is the popular potentiometer. So, concepts with few examples also today's session. Now, the measuring devices, the first one is the ammeter, the current measuring device. Since it is a current measuring device, always connected in series. And this ammeter, a device, should have a low internal resistance. Why? Because since it is connected in parallel, it affects the effective resistance of the circuit, and hence the circuit current will be affected. So to minimize all these errors, for ammeter, the internal resistance should be as low as possible. Ideally speaking, for ammeter, the internal resistance is 0. Ideal ammeter. Now the next one is voltmeter. The potential difference is measured. So voltage measuring device voltmeter and always connected in parallel, because we always calculate PD across 2 points. So it's always connected in parallel. See, when any instrument is connected in parallel, the parallel combination current splitting will take place. And therefore, here voltmeter will draw some current from the main circuits. And hence, it will show some errors. To minimize that error, what we should do? In fact, it should have a high internal resistance, as high as possible. As high as internal resistance, as low as current drawn from the main circuit, and hence the error will be minimized. Parallel combination, parallel connection, very high internal resistance, and ideal voltmeter, the one which we mean does not draw any current from the main circuit, should have an infinite internal resistance. Now let me show some of the examples based on ideal ammeter and ideal voltmeters. Here in the beginning, I will consider a few examples on ideal meters, and also of course let me show some of the examples based on the ammeters or voltmeters with some internal resistance, finite values. Now here I have shown one example, an ideal battery of EMF E, and again its internal resistance is 0 I have taken, and in this network it has given as 4 resistors, all of them shown identical. And this time, ammeters are given in the circuit, and we are asked to find what are the readings of these instrument devices, A1, A2, A3, like that. See, when ammeter, voltmeter examples are given and they are said to be ideal, it is not a new example. It is the case of dividing current or dividing voltage. And we know the rules how to divide the current in parallel combination, how to divide voltage in series combination. The same will be the case, and we write those split values or divided values or branched values as ammeter reading or voltmeter reading. Now any example like this, the first step is to calculate the effective resistance in the circuit. The equivalent resistance of the circuit is a step 1, and after that we use that famous I, the current, is total volts by total ohms. I is equal to V by R. We write the total volts. Why total volts? Yesterday we have shown if it is a combination of 2 or more cells, then we have to consider the equivalent EMF. Thus, I is effective EMF by effective resistance. After that, we will see how this current is branching in the circuit, where the current is splitting. And current split according to I proportional to 1 by R, it will now lead to the solution. Now in this example, see the step 1. Step 1 is 1, 2, 3, 4. In this 1, 2 and this above one. Upper one you will find is 1, 2, 3, all of them are in parallel. Because the same circuit I have written here for your sake. See here, even this is drawn here, then all the three combination, this combination becomes the parallel one, and for this effective, this fourth resistor is in series. Therefore now it is R by 3, and this one is R. The effective resistance is 4R by 3. Now I am calculating the circuit current. The circuit current E effective by R effective will give you 3E by 4R. Now this is what is the current, undivided current, which we call circuit current. And now here you see the branching I splits because this is a branching. This I is now, you look at 1, 2, 3 and all are identical. Since it is identical resistor, the division will also be identical. That is I by 3 through this resistor, I by 3 through this one, and also I by 3 through this one as well. Therefore, this is the current which is I by 3. So I minus I by 3, now it becomes 2I by 3. Is that clear? See, this I is split at this node as I by 3 and 2I by 3. Therefore, now what is this reading of A1? Reading of A1 is nothing but 2I by 3. Now this 2I by 3 at this node, once again split. This is I by 3. So remaining I by 3 is through this resistor. So what is the reading of A3? It is nothing but I by 3. A1 reads 2I by 3. And now look at this A2 here. All this 2I by 3 and this one is again 2I by 3 and this one is I by 3. Therefore, this A2 which is in series with our voltage source, now it shows circuit current. Therefore, now this circuit should give you all the idea. First, after finding the circuit current, you show the current divisions wherever possible. Then that split current or branch currents will give you the ammeter readings. Now the same I have written here. Now A1 which is nothing but 2I by 3, already we have calculated this I, therefore 2/3 is nothing but E by 2R. What is the reading of A2? See there, A2 reads the circuit current, therefore it is I. A3, yes, it's a branch current once again, I by 3. And look here, supposing if you are given another ammeter like this, suppose this is what is A4, then A3 and A4 both will have the same reading because both are showing the branch current I by 3 only. Therefore, the A3 and A4, if A4 is given, the reading will be E by 2R, like this. So next example, I would like to show you a simple circuit with both ammeter and voltmeter. Here again I have shown an ideal cell, ideal battery with ammeter and voltmeter. They are also being ideal given to you. Now in the circuit, what will be the value of ammeter and voltmeter? So as I told you, first let us come to step 1. What is that? First, R effective in the circuit, the total resistance, and hence the circuit current is of step 1. So here, look at this 45 and 15. These two are in series, 45 and 15, no division of current, no splitting of current. So these are series and they give us to 60 and parallel to 30. Hope you can make it out. 60 and 30. Then 60 and 30 in series, therefore it is 30 into 60 by 180, 90, that is nothing but 20 ohms. So 20 ohms is the effective resistance, and therefore I will calculate what is the circuit current I. I is equal to E by R. The total loads 5, the total ohms 20. So this is what is 1 by 4 ampere. And be very careful whenever given some multiples like this, 30 kilovolts, everything, multiples or submultiples, never miss that. Now this is what is I. Once we got I, now this is the circuit current I, show the splitting wherever possible. Now here I will write this as node A, I will write some naming right. This I is now split. I splits at A. So whenever current splits, what is the principle? Current splitting in the inverse ratio of resistance. Now you see current splitting, I will write this as suppose I1 and this is what is I2. I1 in the branch AC, I2 not in the branch AB. Remember, because this 45 and 15 both are in series, therefore the branching is not AB but the branching is ABC branch. So when you are dividing current into I1 and I2, the resistors that you have to consider is in the entire branch. So I1 that is through 30 ohm, I2 is not through 45, rather I2 is now through 60. Therefore now we have to split this current. Split this current I1 and I2. Yes, inverse ratio of. So the total current I times R2 by R1 plus R2. Or simply, why this formula? I will write down I1 by I2 is equal to R2 by R1. What is R2 to be taken here? 60, and this is I1 through R1. If you take 30, then that is what is 2 by 1. 60 by 30. 2 is to 1. So I1 is 2 parts and I2 is 1 part. Therefore, I1 is 2I by 3 and I2 is I by 3. Got it? So I have split current I in the ratio of 2 is to 1. This is 2 part and this is 1 part. Therefore, now what is the reading of A? A reads this I2 because it is in the branch of A, B, C. Therefore, what is the reading of A? So now I am writing A reads I2, that is I by 3. It becomes 1 by 12 ampere. Right? And now, what is the voltmeter reading it is given? Look at the connection of voltmeter. Voltmeter is now connected across this 45 ohm. It's not 4.5 friends, it is 45 ohm. So it is potential difference across 45, and once again I remind you all these examples I am considering meters to be ideal. Therefore, what is the reading of voltmeter? Voltmeter reading nothing but V is equal to IR. I is, as we have told, A, B, C branch contains how much? I by 3, which is, yes, 1 by 12 times 45. So this is what is 45 by 12 volts. Any further simplification of numbers, you can do it for yourself. Like that. So finding effective resistance and circuit current is the key afterwards, branching of current. One more example for your practice I am now showing you as another example. See, here also one more time I have shown some resistor networks. Again, an ideal cell of EMF E volts. Now here I have shown 1, 2, 3 ammeters and voltmeter as well. Now after giving this question, options can be wide open. Different types of questioning can be asked. Here I ask you which of the meters, suppose A1, A2, does they show same reading, or A1, A3 show same reading, or which shows the maximum value or which shows the minimum value, or arrange A1, A2, A3 in the increasing order, decreasing orders, whatnot. A question is wide open and any type of questioning is possible. Now here once again, do remember all the meters are ideal. So here goes our step 1, R effective, total resistance. One more time you will see 1, 2, 3, 4, 5, and also this one is also in parallel. Is it not? Because all of them are connected between these 2 points, common potential point will observe. So how many resistors? 1, 2, 3, 4, 5, 6 resistors are there, right? Therefore R effective is R by 6. R by 6. And what will be the current? Total volts by total ohms. R by 6. Therefore, this will be 6 E by R, the circuit current. So, I, the circuit current we got. Now, the same procedure, branching. Now, since all the resistors are same in magnitude, division, the splitting of current is also same. Therefore, I to be divided into 6 parts, equal 6 parts, I by 6 each it becomes. Therefore, this branch contains I by 6. Therefore, how much here? This branching will be, yes, I minus I by 6. I minus I by 6, that becomes 5I by 6. This one. This 5I by 6, again branching. This becomes, this is I by 6. This is I by 6 and this is also I by 6. Therefore, what is this value? 5I by 6 minus 2I by 6. This is nothing but 3I by 6. Ready? Because this 5I by 6, 2 more branching I by 6 each, therefore 5I by 6 minus 2I by 6, it is 3I by 6. I by 2 will be the reading. Therefore, here I am showing you what is that A1. Now, A1 reads how much? 5I by 6 minus 2I by 6. That is I by 2 it shows. Right? Now, one more time. Again here, branching, same I by 6, I by 6. Therefore, now look here. These two I by 6 will be shown by A2. So, what is the reading of A2? Yes, 2 times I by 6 is the reading of A2. Now, here comes A3. What will be A3? Now, here 1, 2 and one more I by 6. This is also a branch current. This is also I by 6. All 1, 2, 3, 4 branching now will be shown by A3. Therefore, what is the reading of A3? 4 times I by 6. Right? So now we can see different ammeter at different positions. You just go on comparing whether they are showing the same values or maximum value which one, minimum value which one, like that. Now therefore, in such case, what will be the reading of voltmeter? V is equal to IR I am using. What is that I? This is only a branch current of I by 6. Therefore, this is I by 6 times R is the reading of voltmeter. So these two examples are enough to understand any examples based on the ammeter and voltmeters without any internal resistance. Look at this example in which we have used not an ideal voltmeter, an voltmeter with finite internal resistance. Actually, it is not given in the data. How we come to know that? Look at this example. Now, once again, a small network I have shown of resistors. And voltmeter is now connected across this 400 ohms. And he says, voltmeter reads, some number is given like 36 volts. The question is, or the easiest question would be for this data, find internal resistance of voltmeter. First we will do an answer for that. In fact, not asking this internal resistance, but the question can be made a bit difficult by asking if the same voltmeter is connected across this 200 ohm, what will be the reading, like that. So first, whenever a circuit is given, step 1 is, yes, finding equivalent resistance or effective. So here you will find 200, 400 series, and again this is 600 and 1200 parallel, gives us to 400 R1, R2 die. R of to 400. So the total resistance would be all in series 200, 400, 400 and rated as 1000 ohms. R effective is 1000 ohms, and therefore what will be the circuit current now? The circuit current I is, yes, total volts by total ohms. So here comes the current. So current in the circuit is 0.1 ampere. All this is the case when no voltmeter is across any of the resistor. So remember, this is the case when no meter is connected across any of the resistors. Now this is 0.1 ampere. In such case, if a voltmeter we are connecting and that is ideal, what should be the reading of the voltmeter? Supposing if I am connecting across 400 ohms and this voltmeter is ideal, simply I will write what is the current through 400 ohms? 0.1 ampere, use V equal to IR. 400 into 0.1 should give you 40 volts, right? But now, He says the reading is only 36 volts. And that is how we now come to know that this voltmeter is not an ideal. Hope you got how to find whether this given voltmeter or any other example ammeter, which is ideal or not, the reading will give you the data. So here, actually V should be 40 volts, but now V dash is given to be only 36 volts. So what does it mean? The current in the circuit is not now 0.1 ampere. It is not 0.1 ampere. Therefore, I am writing the new current in the circuit. What is that as I dash? So I dash R is equal to 36. Once again, V equal to IR. This time I am writing V prime, V dash. So it's only not I, but it is I dash, the new current, when we are connecting voltmeter across the resistor. So I dash R is equal to 36, therefore I dash is equal to 36 by 400. 36 by 400. That is 0.09 amperes. Remember, what does it mean? This 400 ohms now not carrying 0.1 ampere, rather it carries now 0.09. That is, what is the current through galvanometer? Now, galvanometer, as I have told you earlier, galvanometer when connected in parallel, it draws current from the main circuit. Therefore, what is the current drawn by the voltmeter is our next step, which is nothing but I minus I dash. Yes, 0.1 minus 0.09 is 0.01 ampere is the current drawn by the voltmeter. Now I am writing R is equal to V by I for voltmeter. Because now I have to find the internal resistance of the voltmeter. Therefore, I am using R equal to VI by for voltmeter. V, of course, he says 36 volts, and I, he says 0.01. So this is 3600 ohm. 3.6 kilo ohm will be the internal resistance of voltmeter. Any measuring instrument has two characteristics. One is called range of the instrument. The second one is called sensitivity of the instrument. Not just for voltmeter, ammeter, any measuring device will have range and sensitivity. The maximum value that it can measure, a device can measure, is called range of the instrument. And what is the sensitivity means? It is the maximum possible error using that instrument. Remember, the sensitivity, otherwise called as least count of the instrument, one and the same. But least count or sensitivity does not mean that it is the smallest measurement that is possible with that instrument. No, we should always treat it as the maximum possible error using that instrument. Now, ammeter we have told, ammeter with very low internal resistance we generally use. How to increase the range of an ammeter? Supposing I have an ammeter whose range is 10 milliampere, and at my disposal I don't have any other ammeter, but I want to measure currents of the order of 100 milliamperes or 200 milliamperes. Then this 0 to 10 milliampere cannot be used. We have to use another ammeter, but we are using an ingenious method. By using the same low range ammeter, we can convert that into high range ammeter. So here we are converting low range ammeter into high range ammeter. When doing so, please go through your notebook, we have done it in detail. When low range ammeter is converted into high range ammeter, actually we are multiplying the scale that is given for that device. Scale multiplication only takes place, not that all that high excess currents will pass through the original device. It is no. It only carries the same initial low range current only, but only it is the multiplication factor of the scale. Now here you see, we are now showing a method to increase the range of ammeter, and that is by using a principle of shunt. What do we mean by shunt? Shunt is low resistance, a low resistance. Here itself, when I say low, how much low? It is not low, in fact, it is lower, whose value should be less than the internal resistance of that low range ammeter. Got the point? The shunt, whatever we are connecting, it should always be less than the original internal resistance of low range meter. So a low resistance connected parallel. It is connected parallel. Why? In parallel, the current split will takes place so that we can bypass all that high excess currents. So shunt is always used in parallel. Shunt means always parallel, and it bypasses excess currents. Now here I show the initial range, a low range ammeter to begin with. It's an ammeter whose internal resistance is, suppose I had considered one symbol capital G, and I is its initial range. The maximum current that it can measure is, I have shown it as small I. And it is otherwise also called as current for full scale deflection. Both terms give the same meaning. Now I want to convert this into high range ammeter. Now here you see, here I am showing capital I. Capital I is the final range. I want to now measure as much maximum as that I is the final range. And for that you can see here, S is a low resistance connected in parallel to the given ammeter. Now here at this node, yes, you can see the split of the current. I splits as I and IS. One more time you will see the current to the ammeter is same. Originally it was I, now also it is I only. And the excess current now bypasses through shunt. Once again, this is capital I only, right? So what is that current through shunt? Current through shunt is capital I minus small I. And what will be the effective resistance? G and S in parallel, therefore it is GS by G plus S. So whenever an ammeter is shunted, its effective internal resistance is decreasing. So do remember this expression. The effective of high range ammeter would be G, the original internal resistance, times S, the shunt required, GS by G plus S. Now here, let us calculate at how much shunt we have to use. For that, the expression is current division. Current always divides in the inverse ratio of current. Here I and IS, therefore IS by I, inverse ratio of current G by S, and this is what is giving the result. Shunt is equal to, do the cross multiplication, IG by IS. So this is 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 nothing but capital I minus small I. Very, very popular expression. How to increase the ammeter range and what is the required shunt. See, S equal to Ig by I, capital I for final range, small I for initial range. And now supposing, if I consider that range is made 5 times, 10 times, 20 times, I am taking such number. So for that integral multiple, capital I is equal to n times small I. You do substitution here, this becomes ni minus I. Common terms cancellation, the final result is S is equal to G by n minus 1. Afterwards, we will do some 2 to 3 examples based on this and we'll show the same expression used in 1 or 2 different ways. This time, let us see how we convert a low range voltmeter into high range voltmeter. Earlier, we have said low resistance in parallel to increase the range of ammeter. Here, bit exactly opposite process. What is that? Instead of low resistance, we consider a high resistance, and instead of parallel, it becomes series. A high resistance connected in series with low range voltmeter, then it becomes a high range voltmeter. How? How much? Look at this figure. Now this is initially a low range voltmeter I have taken. This is a voltmeter, low range voltmeter. The current for full scale deflection, the same. Earlier we taken as I, small I, here as well. The current for full scale deflection, and G is the internal resistance. Now this is a low range voltmeter. What will be the initial range? Now it is VI, nothing but PD across the points A and B. So it is VI is equal to I into G, the initial range. Now, we have told high resistance in series. Why? Because we know that in series potential will add up, and that is why here, see, I have taken a high resistance and it is connected in series with the low range voltmeter, and that is why I am using the symbol RS, a resistor in series. RS is the high resistance connected in series. Now, this as a whole, I am marking that, you will see. So, this entire thing now acts as a high range voltmeter. Remember, I have told you, whenever we are increasing the range of an instrument, we are only multiplying the scale of the instrument. Do remember that. Now, what will be the, so this is high range voltmeter. High range voltmeter, what will be its final range? Again, say VAB. It is VAB. So, this time, what is VAB? VAB is equal to V2. Now there are two resistors in series, and in series volts will add up. So what will be V2? I times RS, it is the drop across RS, and plus I times G. Since it is the series, same current, I times G is what is V2. Now here, this expression I have given for RS. I have given for RS. Take I common now. So what is that RS? The final range of the voltmeter by the current for full scale deflection minus capital G to convert the required high resistance in series to convert low range voltmeter into high range voltmeter. Here also I consider that if suppose V2 the final range is N times V1 the initial range, or if I have used I, let me write it as F, okay, VF I will write, okay, final range, I for initial. So if VF is N times VI, substitute here, at least that one line simplification do, you will get this expression RS is equal to G upon N minus 1, where N is the multiplication factor, the times to which the range has increased. And while identifying your options, be very careful. Ammeter, series resistor, that will be a very low value. In the case of voltmeter examples, it will be a parallel combination. The resistors is to be connected in parallel. Earlier in the discussion of measuring devices, a voltmeter is always connected in parallel and it should have as high as internal resistance. Ideally speaking, it should have infinite internal resistance, not to draw any current from the circuit, so that the values are accurate. Otherwise, for all the voltmeter readings, they are erratic. We will always get slightly lesser values because of the internal resistance. Now, ideal voltmeter means internal resistance should be infinite, but practically such devices cannot be constructed. But in a very ingenious method, we are now finding a solution. And that is what is the potentiometer. So potentiometer principle is nothing but the case of ideal voltmeter to measure PD without drawing current from the main circuit. Here I show a simple circuit diagram for the potentiometer. You have already done it, this experiment even in your second PU laboratory. This AB is a long wire, preferably made of manganese wire, because of very negligible alpha value, you remember. So AB is a long wire and that length of the wire I have taken as capital L, and A as its radius, A for radius of the wire, and capital R is the resistance of the wire AB. Now this wire AB is connected to a known source of EMF and write it as EP, and let R small r be the internal resistance of this battery which we are connected. See, point here is I have taken this small a as a radius to avoid the confusion. Here I am referring small r as internal resistance of the battery and A is the radius of the potentiometer wire. Now here this is some additional resistance that I am connecting in series. This is optional. But what is the purpose of this RH? You will come to know in the following discussion. Now this entire thing is what is called as primary circuit. This potentiometer wire and the upper part, this is what is called as the primary circuit of the potentiometer. And now here you will find one more. From this end A, this is I have shown in the form of a cell. Need not be a cell, it is an unknown PD. Remember, this is unknown potential difference, which I am mentioning as ES. This one is known EMF in the primary, and this one is an unknown EMF, and it is in series with a galvanometer, high resistance and jockey. Always galvanometer connected in series with high resistance to protect from high currents and to protect it from damage. Now here, this potentiometer wire and the lower part, this one you call the secondary circuit. So primary circuit and secondary circuit you have two, such that two important conditions for the circuit. What is that? Look at this end A. Now end A, both EP and ES are connected such that A point, the end A should be at higher potential with respect to both primary circuit and as well as secondary circuit. And that is why you can see here, I have connected from higher potential. This is also higher potential. Careful about this point. It is always the end A at higher potential with respect to either of the circuits. And second condition is this EP in the primary should be greater than the ES, the unknown PD in the secondary. Of course, when we say this itself is unknown, how to say that whether how to find or how to guess whether it is EP greater than ES or less than. For that, the trial is there is a jockey. First we press at the end A and then at the end B. If this condition is satisfied, the galvanometer will show deflections in opposite orders, opposite directions, it will show the deflection. Otherwise, the galvanometer will show deflections only in one particular direction. Looking to that direction, supposing if it gives the same direction towards right or towards left, depending upon that direction, we can change the value of EP and thereby we can find this condition EP greater than ES. Now, for the complete potentiometer, the all important formula, you say tool, you say anything, is what is ES, the unknown PD in the secondary. How to find out is X times L. Earlier we have told potentiometer circuit, J is the jockey, press it at end A and then at end B, giving opposite deflections for these two conditions being satisfied. Then the jockey slowly moved from end A to end B, such that for a particular contact, I write it as J, galvanometer shows 0 deflection. Now this length AJ is what is called as balancing length. So now I am writing unknown PD ES is equal to X times L. L is introduced as balancing length, small l. No confusion with symbols. Capital L used for length of the potentiometer wire, small l for balancing length. Now here comes all important about this X. The better we understand about this parameter X, the better will be our approach for the solutions. Any example on potentiometer, understanding of X is very, very important. Now let us talk about this X. X is VAB by L I have taken. This is potential difference per unit length of potentiometer wire. Because AB across which you have applied PD, see remember this one is EP. So VAB, the total volts by the total length of the potentiometer wire, potential difference per unit length, this is what is called as potential gradient. So X is potential gradient. And now this potential gradient is everything for potentiometer. When I said everything, what is that? The range of the potentiometer, the sensitivity of the potentiometer, and everything now depends on the value of X. Now let us see, let us understand more and more about X, because how to find X in different cases of data. Now here I am writing X is equal to, what is VAB? Again V equal to I am writing I is current in the primary, of course, current in primary. So this is current in primary, I times R, V is equal to IR expression, IR by L. This way you can remember. And immediately we will find here that X proportional to 1 by L for a given, yes, for a given EP value, for a given potential difference, potential gradient and the length of the potentiometer wire inversely proportional. So if I want to increase the potential gradient, increasing potential gradient means increasing range. Decreasing potential gradient means decreasing the range. Remember, last time also we have told that any measuring device has two characteristics, the range and sensitivity, such that range and sensitivity are always inversely related. For any instrument, if we increase the range, it is at the cost of it is at the cost of sensitivity. Sensitivity will decrease. Both cannot be increased and both cannot be decreased. One at the cost of the other. Therefore, now in any case, asking about how to increase the range of the potentiometer, then we have to think about X. Similarly, in the case of sensitivity also. Such that, now what is the principle? Range proportional to X and sensitivity inversely proportional to X. It will be the principle for our solution. Now here you see, I am writing for again I again total ohms by total ohms. As I have told you, I is the current in the primary circuit, therefore primary ohms, EP, and what are the total ohms here you can see? Capital R, resistance of the potentiometer wire, small r, internal resistance of the source in the primary, and RH is the additional resistance I am using. Why that additional resistance I am using? Because you will find, see here, capital R plus RH, the additional resistance. Because the value of X, we can have a desired value. I can increase or decrease by the choice of RH. Instead of changing every time EP, the potential gradient can be fixed as a desired value by fixing the values of RH. And that is why I have told you that RH is optional. If I have to increase or decrease potential gradient, I will make use of that. Now you see, this is what is X equal to EP by expression. Of course, R by L is there outside. Remember, this is the maximum denominator term that is possible. Because all the cases RH is not there, all the cases internal resistance is not there, supposing. So whenever I am using capital R plus small r plus RH, this is the maximum value in the denominator. Therefore, this is the expression you can say the minimum potential gradient. I am writing it as X minimum potential gradient. Right? Now similarly, what is the maximum potential gradient? I put small r equal to 0 and RH equal to 0, and that is why this expression X is equal to EP by L, this will be maximum potential gradient. Now, one more expression I am showing you. See this IR by L, I am taking this expression. This is what is I for the, of course, primary current, R for resistance of the potentiometer wire. Now I am using the same. Earlier we have talked about resistance of a wire. You remember? Write that expression I. Because if you do like this, it is not a memory. Otherwise, don't think that we need to remember all these many formulae. No, it is only simple expression. Afterwards, let us use our fundamentals. What is capital R resistance of the wire? You remember rho L by capital A is the resistance by L. What is I for? Current in the primary. Rho for resistivity. This is resistivity of the potentiometer wire. L for length of the potentiometer wire. A for cross section. Cross section, shall I write it as pi a square because small a I have taken as the radius. Therefore, now I am writing X is equal to I rho by A. This is I rho by pi small a square expression. Now this will tell you all about the X now. What is that X? X inversely proportional to, and let me write those results. Okay. Now come back to this side, and now you will find all important points for the value of X. Potential gradient. On what factors does it depend? Does it depend? Now you can say x proportional to 1 by L. Of course, x proportional to 1 by L for a given ET value, for a given voltage across AB, we have said. X proportional to 1 by L is one result, you can make it out. And x proportional to I is one more important result that you can make it out. Look here. X proportional to I, x proportional to 1 by L. And here what is that? Observe. X proportional to 1 by capital A. It also depending upon the thickness of the potentiometer wire. You will find the examples where after finding the balancing length, small l, now he says it changes in the potentiometer wire. Supposing length of the potentiometer wire changed or thickness changed like that, or else any other potentiometer with different dimensions, what happens to this balancing length? So in finding all such examples, not only that and any other example, potential gradient is an important parameter to understand. So x depends on all these things, and any other things also you can go through these things and you can find on which factors does it depend. Popular experiment, potentiometer experiment to compare EMFs of two cells. A circuit, earlier we have used the same circuit here. Now here, this experiment can be done in two ways. First one, in first method, we will use one EMF at a time. We are given two EMFs, E1 and E2, both unknown, or maybe one is known, the other one is unknown, like that. Now, we are using only one EMF at a time. So first I have placed here E1, and of course all those conditions being satisfied. Now I get a balancing length AJ for a cell of EMF E1. I am getting balancing length as L1, therefore E1 is equal to XL1, the potentiometer principle. Now E1 is now replaced by E2. Remember, it is only replacement of the cell. Another EMF E2 replacing E1, again balancing length L2, and therefore E2 is equal to XL2, and therefore the simple result is E1 by E2 is equal to L1 by L2. L1 balancing length for E1 alone and L2 balancing length for E2 alone. In another method, where you are given an example in which both the cells are used at a time. Now here I show E1 and E2 both are used, but it says series connection, and the balancing length is L1. Remember, L1 is the balancing length for both E1 and E2 connected in series in the secondary circuit. Therefore, now I am writing the total EMF, cells, series, parallel was the topic yesterday. So E1 plus E2 is XL1. Okay? Now, one of the cell is reversed. That is now, after that, second part of the experiment, E1 and E2 are now placed in opposite series. One of the cells is reversed in the polarity. Then I am writing opposite series principle. Yesterday only we have discussed that will be E1 minus E2. When I say E1 minus E2, I mean that E1 is greater than E2. If it is E2 higher value, E2 minus E1, like that. So higher minus, now I have taken E1 minus E2, the net EMF equal to X L2. Again, take the ratio of these two. What you get? E1 plus E2 by E1 minus E2 is L1 bar L2. Now use your component dividend method. You have this expression E1 by E2 is equal to L1 plus L2 by L1 minus L2. Now look at this point. E1 E2 in series, the balancing with is L1. E1 and E2 when they are opposite in series, that value L2 of the balancing length is less than L1. Why? Because what was the rule for the potentiometer? You remember, we have said ES is equal to XL, such that L proportional to ES. Yes? More EMF, more PD, more balancing length. Now here, when they are kept in opposite series, the net EMF is decreasing and therefore L2 is less than L1. So this is also a very popular expression. Remember, comparison of cells in two methods. Each one used at a time or both used at a time.